I am Dr. Rashi Tyagi, working as an assistant professor at Chandigarh University in UCRJ department. So today our session is about innovation in electrical discharge coating. So we will discuss the innovation in electrical discharge coating. So these are the presentation outline: introduction, literature review, objectives, methodology, experimentation, resultant discussion, conclusion, future scope, and references. We will start with the introduction. So we will discuss the principle of electrical discharge coating. Basically, what is electrical discharge coating? Electrical discharge coating is a process of depositing tool material over the workpiece surface by utilizing the spark discharge in EDM. So basically, we are performing the electrical discharge coating in EDM machine. Electrode, as you can see, this is the green compact electrode, which has a loose bonding between its particles because it is made from the powder at a low compaction pressure and temperature. As we have compacted the powder, then we have made this compact, so it has loose bonding between its particles. So it becomes easy to deposit the workpiece surface by utilizing the spark discharge in EDM. Basically, reaction takes place between material that comes from the green compact tool, the dielectric. Basically, in EDM, we use dielectric oil as a medium, and by applying the voltage and current, the spark discharge takes place. Due to heat of these sparks, the material from the green compact electrode melts and deposited on the workpiece surface. So this is the process of electrical discharge coating. Basically, difference between electrical discharge coating and electrical discharge machining is that in electrical discharge coating, we are depositing the compact material, but in machining, we remove the material because tool is hard. But in EDC process, makes it possible to deposit its material over the workpiece surface. In EDC process, the tool to a negative power supply and the workpiece is connected to positive power supply. So this is our process by which we will further discuss its advantages, disadvantages, and how it helps in improving the surface characteristics of any workpiece or any substrate. Of EDC process. Basically, EDC is a effective process because just by utilizing the powders, you can deposit the material. So area over the workpiece surface can be coated easily. It means any small surface can be coated by using electrical discharge coating process. Basically, multiple materials, including composite coating, can be produced in one go. It means you can use many materials, and by making the composite, you can deposit on the workpiece surface. Machining and coating can be done simultaneously. If you are using the hard material, then you can also perform the machining and coating together to improve the surface characteristic during machining. Coating on very hard material, coating of very hard material is possible. It means any hard material can be used in this setup. Basically, no high temperature vacuum surrounding is required as it is required in other processes such as laser cladding process or any other process. Capability to generate a thick coating layer. It means you can generate thick coating layer up to 2 mm thickness. Even if you want to deposit it, you want to repair the component, you can deposit the thick coating onto the surface. Gap in EDC. Basically, many research was done on the EDC process, that is given from 2002 to 2003, then 2010. Basically, in all these research, it is found that they using the titanium, copper, iron, tungsten carbide, titanium, graphene, and it means they are using depositing the hard coating, but there is no soft coating done by this process. They improve the wear resistance of the workpiece surface and tribological behavior of the surface by using the different hard tools. In this, titanium, carbon nitride, silicon carbide, copper, and stellite can be used. So in these are the findings of the research gap, and there is a research gap in which we have found that there's a cracks and pores formation was there. Cracks and pore formation are there. Also, some of the research does not discuss the wear and friction behavior of the coating. So what are our objectives? It means what we are doing. By doing the research gap, we have seen that there is no soft powder use that I've already discussed with you. So in this process, we are using the solid lubricant coating. That is the solid lubricant WH2, HPN, MOS, yani ki molybdenum disulfide, tungsten disulfide, and HPN. So we are using these powders to improve the characteristics of the mild steel surface. through electrical discharge coating process. Mechanical and metallurgical properties of the coating. So in this, we will analyze the different characteristics of the properties of the deposit layer with respect to input parameter. Input parameter means EDM parameter that we are changing. Evaluation of corrosion resistance, tribological performance, and wettability of the deposit layer. So we will discuss how the EDC process improves the corrosion resistance, tribological performance, and wettability properties of the deposit layer. Lubrication, basically these are the WS2, MOS2, and HBN lubricant, and how it works. They have the laminar structure. It means that these are the layers that are in laminar form. They have low shear resistance between these. There are low shear resistance between these layers, so that they can slide over each other. If they slide over each other, they provide the low coefficient friction against other surfaces, as you can see. As you can see, this is so there is a large area in this figure. You can see there is a large area, so there will be low shear stress because shear stress is equal to force per unit area. So if area is large, because these lamina align themselves in the direction of motion, so area becomes large, then shear stress becomes small. So there is a low shear stress, so that they can provide the low friction coefficient. So these are the structure of the WS2, MS2, HBN that we have shown, that they have the laminar structure, the hexagonal structure. So this structure helps in improving the tribological properties, or you can say coefficient of friction or wear properties. That we have used initially we have fabricated the green compact tool, then we have performed the electrical discharge coating, then we have analyzed the quality of coating. Basically, tool is fabricated by using the different powders. So this is the powder that we have used. We have mixed this powder in the mortar pestle. So after performing the powder mixing, we have compacted it in the hot mounting press. In the hot mounting press, basically used to compact the powder. This is the upper and lower dies. Basically, there are two dies, upper and lower dies. In between, the powder is placed, and then compaction pressure is applied and heat is applied, so that they make a bond between the powder particles. Then this is the green compact that we have obtained. After obtaining the green compact electrode, it is called green compact because it is made in between the closed dies. So we are using the term green compact. So this green compact tool is tested with the rod to use it finally in the EDM machine. So this is the process of electrical discharge coating. The material carbide, this is all we have already discussed. This is the coating preparation phenomena and how the coating forms. So this is the quality of coating that you can see. We have performed the FESM analysis to observe the cross section of the coating, top surface morphology, contact angle, and wear resistance. That we will also discuss. In further slides. Of green compact tool, how we have prepared the green compact tool. So these are some constant input parameters that we are using. That is solid lubricant, powder material constant. We are using WS2, MS2, HBN copper powder. This is the average powder particle size that we are using. This is the sintering temperature applied in the hot mounting press. Basically, these are the hot mounting press parameter in which we are making the green compact tool. This is the pressure. This is 200 kg per centimeter square. Heating time 10 minutes, cooling time 5 minutes. These are the variable input parameter, that is we are changing the powder mixing ratio in different ratio. First of all, we are using all together copper, WS2, MS2, HBN, and in other green compact we are using different. And it means we are taking copper WS2, we are taking copper MOS2, we are taking copper HBN in these mixing ratio. By using these mixing ratio, we have prepared the green compact tool. Basically, this is a solid lubricant. This is the HBN powder that we are using. This is the copper powder. It is an example that this is a solid lubricant. This is the binder. So when we are mixing it, we are making the green compact tool of this size, and then we are making the two electrode extraction that we have already discussed in methodology. The experimentation. So basically, experimentation is performed as we have discussed in EDM. And these are the constant input parameters that we are using. Material the work is mild still. These are dimension, machining time 4 minutes, polarity negative, positive. Basically these parameters 4 minutes 29 microseconds. This is pulse on time, time for which current is allowed to go. So through the electrode, this is a 29 microsecond, and gap voltage is a 40 volt, and peak current is varied 4 ampere to 10 ampere. Basically, and duty factor 30 to 90%. So basically, these parameters are decided by performing the trial experiment that we have performed. So the arrangement of setup that we are using, the green compact tool that is hold in this tool holder, and this is the magnetic base which is attached to the clamping vise. The clamping vise in which we have attached the workpiece surface. So this is a setup that we are utilizing. After the coating, it is observed that there is a holes in the electrode surface after deposition. Holes in the electrode surface after deposition, and there is a deposited layer that we have obtained. So the electrode surface after experiment, we have decided the trial I have told you that we have performed the trial experiment. So below 4 ampere current, it is observed that there is no deposition. It means tool material doesn't get melt and doesn't get deposited on the workpiece surface. So below 4 ampere, we have not performed the experiment below 4 ampere. Then we have go forward above 4 ampere. So this is a reverse polarity that we are using. By using a reverse polarity, it means tool is connected to negative, as I have told you in the first slide. So that negative polarity allows large amount of deformation of the tool from the tool surface. So this is a copper HBN ratio. Above 10 ampere current, tool gets melted. So then you can see at high coating time that we are using the 4 minutes above high coating time. So we did not perform the electrical discharge coating because tool gets erupted totally. So at low compaction pressure, temperature, we are using the low compaction pressure below 200 kg per centimeter square, temperature below 130 degrees centigrade. The HBN tool gets big. So this is a higher pulse on time and voltage at constant current that we are using. So these are the electrode surface by which we have chosen our parameters. Experimental table in which these are the powder mixing ratio that is varied, peak current 4 ampere to 10 ampere, duty factor 30%, 50%, 70%, and 90%. These are the fabricated coated sample images. As you can, these are 36 experiment that is performed using copper WS2 tool and copper MOS2 tool. 36 experiment that we have performed that I have shown in these are surface after the coating. Result and discussion. Initially, we will discuss the investigation on coated surface characteristics. So, here the cross-section morphology of coating at different peak current. As you can see, this is for MOS2 plus copper coating. This is for WS2 plus copper coating. And this is for HBN plus copper coating. So, we have observed the result at different peak current. As we have varied the peak current from 4 ampere, 7 ampere to 10 ampere, in which we can observe as we are increasing current, coating thickness increases. As you can see in all these results, we can observe that for WS2 copper coating and HBN2 copper coating, as we are increasing the current, we are obtaining the higher coating thickness 0.37, 0.61, 0.66. Similarly, in the MOS2 and HBN coating. Why? Because when we are increasing current, there is a large amount of heat goes into the tool surface, and more amount of tool gets melted, and more metal gets deposited over the workpiece surface. So we are having the high thickness at high current. This is a surface morphology of coating at different mixing ratio. It is observed that when we are changing the mixing ratio, there is a change in morphology. It is observed that when we are using the high amount of MOS2 and low amount of copper, basically copper works as a binder. Copper works as a binder. So if we are changing the percentage of copper, or we are using low amount of copper, there is a MOS2 is basically insulating material. So if we are using a low amount of copper, high amount of MOS2, the electrode becomes insulating, less conductive. So if it becomes the less conductive, more insulating, so it becomes difficult to deposit the metal on the workpiece surface. So non-uniform deposition was observed. Although when we are increasing, when we are using MOS2 copper 50 to 50, there is a good amount of deposition can be observed, although some pores are there. Similarly, we can observe WS2 and WS2 copper coating, in which we can observe the very less amount of pores observed in 60 to 40 coating. So we observe that there is a large amount of electrode erosion at this mixing ratio. So large amount of deposition takes place at this mixing ratio. So these are for HBN is to copper coating, in which at HBN 50 to 50 we observe the good surface. Morphology of the soil lubricant coating at different duty factor. Basically, duty factor determines the efficiency of coating. So we observe that when we are increasing the duty factor up to 50% for MS2 copper coating, there is a good surface obtained. Although when we are increasing the duty factor to 90%, only arcing obtained, because basically duty factor is the pulse on time to the total cycle time. Pulse on time divided by total cycle time. So when we are increasing the pulse on time, there is a large amount of current goes through the electrode and more amount of material gets eroded from the tool surface. But it becomes it becomes in the gap, it becomes in the spar, it accumulated in large amount in the spar gap. So it will not flow with the dielectric. So there is a arcing takes place. It means same spark generated at the same location, because there is a large amount of material at between the spark gap in the spark gap. So it is observed that at 50% duty factor, there is a good surface obtained. Although when we are increasing the duty factor from 70% to 90%, only arcing, mainly arcing is observed. So void formation and big pores and void, some defects are observed. Similar results are obtained for WS2 copper coating, and for HBN2 copper coating at 70%, we obtained a good surface. The micro hardness and bigger micro hardness machine. There is the micro hardness that we have obtained for different coatings. So you can see there's a very low hardness obtained by using low lubricant powder. Although for parent material, it means which was mild steel, we observed hardness was 180 HV at 0.2 kg load. But for solid lubricant, you can observe there's a low hardness below 180, that is 80, 60, 80, 65, 67. There's a different hardness we obtained. These hardness are due to solid lubricant powder. Basically, solid lubricant and the soft powder that results in low hardness. The hardness are very low. These are the soft lubricants, MO2, HBN that we are using. So hardness becomes low. That also proves that there is a solid lubricant deposition on the workpiece surface that can improve the tribological properties. So these are the micro hardness that you can see at different duty factors. The micro hardness different colors. So at different duty factors, you observe that there is a low hardness obtained by increasing the duty factor at 30% to 50%. Similar result is observed for copper WS2 coating and copper HBN coating. By increasing the duty factor above 50%, it is 70% and 90%, then hardness is. Why? Because the 50% duty factor, as we have already discussed, that there is a large amount of deposition. So the hardness becomes low at 50% duty factor. So this is the indentation point for the proof that we have obtained that low hardness, that is actually 45.49. That's the indentation point that we have captured the image in weaker hardness machine at 0.2 kg load. Discuss the chemical and corrosion resistance, and we do the chemical and corrosion resistance analysis. So we have performed the EPMA mapping that is used to denote the spatial distribution of the coating element, that is MO, copper, sulfur. So by these images, it is for E, F, G, as this is for WS2 copper, I, G, K, L, it is for HBN2 copper. In these images, we observed that there is a uniform deposition of the metal on the workpiece surface. So the dark orange part shows the MO, copper, F. Similarly, dark orange part shows the tungsten, copper, sulfur, and boron, copper, and nitrogen. So we can say that there is a uniform deposition of the tool material on the workpiece surface. So then we have the chemical state analysis. In chemical state analysis, we have shown that there is a total amount of deposition of MOS2 particle. It means the MOS2 element does not break into molybdenum oxide or sulfur oxide. That can be proved by chemical state analysis, because in laser grading process or other processes, it is observed that MO and sulfur get disintegrated into molybdenum and sulfur, and they form oxide and some other compound. But in EDC process, this MOS2, HBN, and WS2 does not disintegrate, because we because we are using the low pressure, so they does not disintegrate, but total amount get deposited on the workpiece surface. That can be proved by these images, that is obtained by XPS analysis. And by previous study, we have proved that there is a total deposition of MOS2, WS2, and HBN. Corrosion rate measurement that is performed. This is the corrosion rate formula that we have used to perform the corrosion resistance analysis. This is the setup that we are using: spindle that is attached to coated sample, then NaCl solution that we are using, the 1 centimeter square area that we are using, and we are performing it at 140 hours, and density is calculated by Archimedes principle. So the stand that we are using is spindle. First of all, we have conduct the corrosion resistance analysis at stagnant solution condition, and then we are using the motor, then analysis performed at flowing water condition. We are obtained at a stagnant flowing water solution in different coatings. So the minimum corrosion rate is observed at HBN is to copper coating, at stagnant, at flowing, at both conditions. So these are all coatings showed the less corrosion as compared to mild steel. Wettability and typological properties of the coating. Wettability basically determines the ability of the liquid to wet the surface. So we are wettability is determined by the measuring the contact angle. So contact angle is measured in the dot shape analyzer. This is a needle diameter and droplet volume that we are using. So wettability is determined by using those two models. First is Casey-Webster model, and second is Wenzel model. This is the Wenzel model and this is the Casey-Webster model. So wettability depends on the surface roughness of coating that we will discuss later. So we will discuss how wettability is affected by surface roughness. We have the surface morphology of the coating that is shown that there is a large contact angle obtained. Large contact angle means above 90 degrees it is hydrophobic, above 150 it is super hydrophobic. So this is a large contact angle that we have obtained by increasing by changing the mixing ratio. As you can see, it is surface 40:60 and this surface is 50:50 mixing ratio. So when we are increasing the HBN, large contact angle is obtained because HBN has an ability to repel the water. So if it will repel the water, this large contact angle is obtained. Similar result is observed in this, as you can see for WS2 copper coating when we are increasing the mixing ratios 40:62, 50:50, to 60:50. So we are using we are getting maximum angle at 60:40 mixing ratio. Why? Because of the large amount of nodular structure. That means protrusion that is according to Casey-Webster model. Because Casey-Webster model determines that if there is a large amount of porosity, then water droplet will rest at the top of the surface. It will wet the surface. If it will wet the surface, it will go through the rough surface. But in this, there is a nodular protrusion that we can assume this type of protrusion that is on the rough surface. So this is a protrusion that is rough surface that results in repel the water and large contact angle is obtained. Basically, parent material mild shows contact angle of 78.7 degrees. But for WS2 copper coating, we have obtained a large contact angle. Similar result is observed for WS2 copper coating. Although there is a large amount of lump formation and big pore formation can be seen that results in repelling water and maximum contact angle of 165.6 degrees. Energy calculation. Surface free energy defines the excess energy that a surface have as compared to bulk surface. That is determined by the surface free energy determines basically biomedical properties, self-cleaning property, and wettability of tribological proteins. If the liquid will repel by the surface, then surface free energy will be low. It means it will provide the cleaning process in the biomedical component or wettability of the tribological properties. These are the two liquids that we are using: distilled water and diiodomethane water. So if we will see what is the surface energy, if it is large, then it will absorb the water. It will, if there is a low, it will repel the liquid. So this is a formula that we are using. We are using the surface energy of dispersive component, surface energy of the solid, the surface energy of the solid, surface energy of liquid, or polar component. Basically, these water and diamethane liquid have two components, that is dispersive and polar component. First will repel the water, then will absorb the water. So by using these values and by calculating the surface free energy of the solid dispersion of polar component, we combine this and by taking this equation, we obtain the total surface free energy of the surface. So taking the total surface energy, it is observed that the surface energy of the coating in which the minimum energy is obtained for WS2 copper coating. As you can see, for coating at 60:40 ratio, because this coating at A3 is the mixing ratio 60:40 for WS2 copper coating. So it shows the minimum amount of surface free energy. It means it can show you the good self-cleaning property and tribological property, because it has the lowest surface free energy among all the coating. So we have also observed total surface free energy with time, in which we can observe that as the time increases, surface free energy increases, because surface become losing its property and it will repel the water. So water droplet will absorb. So it will this is the surface energy for parent material. So all these surfaces have low surface free energy below 43.92 as compared to parent material. Wear and friction behavior of the coating, the parameters that we are using. This is the setup that we are using, that is pin on disc test setup. The formula of specific wear rate while calculating the weight loss, mass loss, sliding distance or the sliding distance of wear track and the load, we obtain the wear resistance. This is the prepared pin. This is the coated sample that is attached to the pin. This is the chemical configuration EN31 steel disc. There is the counter disc as shown in the figure. So this is the material component of this. We are using the EN31 steel disc. This is the coated sample that we are using. By capturing the data on the computer, we have obtained the coefficient of friction and wear in different coating, in which we can observe that all the samples showed the low specific wear rate, the coefficient of friction. All the samples show low coefficient of friction as compared to mild steel. This is the coefficient of friction for mild steel surface, and all other samples showed low coefficient of friction as compared to mild steel surface. As we have also shown that these all are the low amount of surface free energy. So they are showing the good tribological property. Similarly, for WS2 copper coating, low amount of, you can see in the WS2 copper coating, there is a minimum wear resistance that is observed for WS2 copper coating. This because this coating also shows low surface energy. So we have established the relation between surface energy and wear rate. So it can be shown by this figure that mild steel surface and the larger surface energy, and all the surfaces are low energy. This is the comparison of wear mechanism. As you can see, this is a mild steel surface. This is the MOS2 copper surface, WS2 copper surface, and HBN copper coating. So in this favor, it is observed that the abrasive groove that is formed. So you can see that for minimum abrasive sliding direction can be seen. This is the surface that showed the lowest wear resistance. So this is the surface captured after the tribological test. So we can see deep grooves in HBN copper coating, and also deep grooves in sliding direction MS2 copper coating, but low amount of deep grooves as WS2 copper coating. That also proves that WS2 copper coating has low wear resistance. Conclusion that we have established: pure solid lubricant coating was not possible as the powders are non-conductive and very dry. So copper was mixed as a binder. Basically, solid lubricant coating was not possible because these solid lubricant powders are non-conductive. So copper was mixed as a binder to make the green compact tool conductive. Basically, morphology of coating can be varied. So EDC process with proper control of input process parameter. As we have seen that at the large amount of peak current, large coating thickness was obtained. So we can control the coating characteristics by controlling the process parameter, which also determines the porosity in the coating, because large amount of tool erosion results in large amount of deposition, and large amount of tool erosion will be possible at high current. Maximum roughness obtained as MS2 copper coating, as we have seen that large amount of nodular protrusion can be seen at MS2 copper coating, resulting large contact angle of 165 degree. All the coatings showed low degree of wear as compared to base material, but we have already observed. Wear rate was lowest in WS2 copper coating, which also showed the lowest surface energy at this mixing ratio. Among all the prepared coatings, the prepared HDN copper coating has been excellent corrosion resistant because it has a proper corrosion resistant property. HDN has a corrosion resistant property which results in large amount of corrosion resistance as compared to WS2 copper and MOS2 copper material because it depends because corrosion resistance depending on the basic nature of solid lubricant. So work, they are the future scope of the work, post processing of EDC layer to reduce the surface roughness in EDC. Basically, EDC process a large surface roughness which cannot be used in some industrial components. So post processing required. Post processing can be done by performing the EDC process again on the obtained surface. Then application of EDC over the complex shape. Basically, as we can change the shape of the tool of green compact. So if we are using the complex shape tool, it is possible to coat the complex shape workpiece. And study of EDC process with green compact tool through the development of numerical model. Basically, there is no numerical model developed to observe the heat transfer effect and current effect. So these things can be done in future. And that is, first is reduction of surface roughness. Second is complex coating over the complex shape tool by making the complex shape tool. Also numerical model by using the different numerical model, we can obtain the optimization of the process that we have utilized.